this recording, and I guess I didn't. Oh, there's a lot of things I haven't done, and I really felt like I was on top of things, if you can believe that. If you can believe it. Where is it? There. Open. New note. Report. Okay. So today we're going to talk about Boolean algebra. I'm breaking it up into two parts, which is probably, hopefully reasonable. Let me turn this. Which one? I want just these out, but can't have it all, I guess. So Boolean algebra, we're gonna talk about disjunctive and conjunctive normal forms. Have you seen that before? No. Okay. Phew. So boring when you've seen stuff before. Well, for me, I guess. For you, it's all fun and easy. And then part 2 is going to be car now maps, which we'll do on Monday. So in terms of kind of the layout, my plan so far, or right as it stands, I guess, is get some lines on there. So on Monday, on Monday, 27th, we're going to do car now maps, which are an extension of what we're doing today. So more Boolean algebra. It's just a way of organizing our work. And so pretty straightforward once you get it, I feel like, although I really struggled initially with it, but now I think I get it. So that's what we'll do on Monday. And then on Friday, which is December 3rd, no, can't be. Yeah, 2nd. What is the 1st? I was way ahead. Nice. I'm planning on doing final exam review. So just running you through what types of questions, how many, that kind of thing. And so you can bring your questions. And then on the following Monday, which is our last class, technically, but you've been so good that if you want to, we could do no class. Have a break. You deserve it. Okay. I'm happy to show up, but sometimes it's nice if you feel like, oh, I could go, but I've got all this other stuff to do, blah, blah, blah. And so that's December 4th, right? Everyone else has been canceling classes, and we can too when it really pays off. How about that? So that's my plan. Oh, final exam. Whoa, very different from what I meant. Final exam review. That's important. Otherwise, it means something completely different. Okay, so that's my plan. The final exam is on the 18th. I feel like it's a Monday or a Tuesday. It's a Monday. Not that it matters, but so I don't put the wrong thing. From 9 to 12. Let me just confirm though before. All the sections are writing together in one room, or sorry, across 2 rooms. But you'll see when you get there. Yeah, so it's a Monday 9 to 12 in E308. Yeah, and E310. So you'll go there and there will be exams laid out with my name on them, some with Paul's name on them, and some with Susan's name on them. You should probably pick one with my name on it because Paul goes really hard on logic and we didn't. Yeah, yeah. And so you should probably choose my exam for that reason. Because it caters to how we approach the course. And so so you want to make sure that you go for the right exam. But yeah, so they'll be spread out across the rooms and we'll all just be floating across the room. So if you have a question, they'll be able to call me over if I'm not in the room or whatever. So nice. Any other questions about the final exam? I'm going to keep it to a minimum. How many marks? I don't remember off the top of my head. Probably like 10 out of 110 or so. Yeah, keep it under control. Okay, any other questions? Before we start, 15 minutes late. Not late, well, yeah, late, but also okay. So to clarify, Boolean versus binary. We talked about binary last day, but Boolean is limited to 1 bit, so a binary digit. So B can really only be 0 or 1. And from last day, very similar in Boolean addition and multiplication, we're going to set it up the same way. If I'm adding 0 and 0, I get 0. 0 and 1, I get 1. 1 and 0, I get 1. And 1 and 1, I get 1. Because my only options are 0 and 1. Whereas before, we had that be 10 or 1, 0 last day, right? And so now in Boolean addition, since we are limited to B, which is on the set of 0, 1. I feel like these are easier to work with than the previous ones, so that's nice. And if we're multiplying 0, 1, 0, 1, it works exactly like regular multiplication. 0 times 0 is 0. 0 times 1 is 0. 1 times 0 is 0. The only time it's 1 is when it's 1 times 1. As a reminder about the complement, we saw the complement back in logic, right? But when we have a bar over something, then it's the complement of 0. The complement of 0 is 1, so it's the opposite. Now, in terms of some notation here, we could have, so some of the assignment questions might use a tilde 0, which means the same thing, which is 1. Or some other notation is a 0 prime is 1. So the prime can be confusing if you've done calculus, right? But context will tell you that it's not the derivative. And so just different notation. Can I see that one graph that you have? This one? Yeah. You bet. So if we have some variable x, then if x can only take on 0 and 1, then we call it a Boolean variable. And what that means is, okay, x can be 0 and 1 and x can be 0 and 1. But what happens is if I have x plus x, then I get x. So we can look back here. If x is 0, right, then 0 plus 0 is 0. 1, so if x is 1, I have 1 plus 1 is 1. So here, this is the same as saying 0 plus 0 is 0, and 1 plus 1 is 1. Right, we saw that earlier. Same thing with x squared, so x times x, same thing as up here. If I have x be 0 and I'm multiplying, 0 times 0 is 0, and if x is 1, I get 1 times 1 is 1. And so 0 times 0 is 0, and 1 times 1 is 1. Can't remember if we've used the for all notation before. Might have been a while. But this upside down A is for all. It's just shorthand. So for all x in B, for all x in the set B, right, and it's referring to these x's here. Right? So this is always true as long as you're working in 0, 1. So if x and y are Boolean variables, so now we're extending them to be able to be different from each other, then x plus y is 0 if and only if, more shorthand, I guess, if and only if, which we saw back in logic, but it's been a while. The only way I can have x plus y be 0 is if they're both 0, right? If and only if x equals y equals 0. Same thing, x times y is 1, if and only if x is y, which is 1. We're going to use this notation, but I'll try to avoid it because I find that it's a little bit confusing, or more confusing than it has to be. But a function f, which goes from bn to b, so you read it as from bn to b, is called Boolean, or a Boolean, or a switching function of n variables. So usually we're going to focus on 3 or 4 Boolean variables, and we're going to use w, x, y, and z as our Boolean variables. And for 3 variables, we're going to use x, y, and z just to standardize things. So then we drop the w. So usually how we write this function is we write f of x, y, z, but we're allowed to have more variables. But for us, and just as a heads up, on the final exam, it's going to be 3. And you'll be grateful for that once you see 4. Okay. So it will be very reasonable. 3. We're going to look at 4, but it gets a little bit wild. Okay. So let's see here. What if we have something like this? This doesn't really look like an example at the start. If I let f be some function that takes something from B3, so from 3 variables to 1, then I have, what that means is that I have 3 variables here. So like I said, it's kind of extra notation that we don't really need, bogs us down a little bit. So I'm just going to start at the function, but if we were saying it properly, we would have this, but I'm going to exclude it, which I think I did maybe in the next example or so. And so we're just going to jump from here, but I trust that you can read this function notation and see that there are 1, 2, 3 variables, which is going to be important later on. Okay, So we want a function in terms of x, y, and z where it equals x times y plus z. That's kind of weird. We're letting x, y, and z be Boolean variables. And so what we're going to do is this Boolean function, we're going to evaluate f for each of the possible assignments to the variables x, y, and z, which to me sounds like a truth table. And it is. So if I have 3 variables, searching our memory palace to back to truth tables, then I have 8 possible assignments, right? Which I then take and I split up the first group, and I have x, y, and z. I'm going to construct my truth table. And if I need 8, which I do, then I'm going to start with 4 zeros for x and then followed by 4 ones. 1, 2, 3, 4. 1, 2, 3, 4. And let me just bump this up a smidge. Then I do it again, but I split each of these groupings in half. So then I get 0, 0, 1, 1, 0, 0, 1, 1. Z, if I want all the possible combinations, is going to be 0, 1, 0, 1, 0, 1, 0, 1. Now I have all the possible combinations of x, y, and z. Nice. Little truth table refresher. So now what we're going to do is we're going to look at x times y, remembering that this is Boolean multiplication. So I'm going to make an x times y column, and then I'm going to take x times y, right? So 0 times 0 is 0. 0 times 0 is 0. 0 times 1 is 0. 0 times 1 is 0. 1 times 0 is 0. 1 times 0 is 0. I hope someone walks by. 1 times 1 is 1, and 1 times 1 is 1. Imagine walking by. Is she just saying that over and over again? I am. Different order, though. Okay. Now we have our truth table for x, y, but we wanted x, y plus z, right? So we're building out this x, y plus z. And so now I'm going to make a new column of x, y plus z. And just as a side note, when you're multiplying, you can read it as and, x and y. And then, which means that addition is or, right? And so now you have x and y or z. If you find it helpful, might not. If you don't, you can ignore it. So now I have x, y, which I want to add to y, or z, sorry. And so now I'm going to have 0 plus 0 is 0. 0 plus 1 is 1. 0 plus 0 is 0. 0 plus 1 is 1. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1, and 1 plus 1 is 1. That's where I got those hallway lurkers. 1 plus 1 is 1. There's guaranteed no one in the hallway. Let me just make sure I got all of them. 1, 2, 3, 4, 5, 6, 7, 8. Nice. Okay. Which means that f of x is going to be true wherever there's a 1, right? So that combination of x, y, z, which means that the first combination where it's true f of x, y, z is when x is off, y is off, and z is on. But overall, this is how the function behaves, right? So I'm not gonna single anything out, but this is the function f of x, y, z, right? How it behaves is equal to x, y plus z. Nice. It's been a while, but truth tables are pretty fun, I think. I'll highlight this because it's worth remembering that you have the total number of rows in a truth table will always be 2 to the power of n, where n is the number of variables. Right? And so I've already said that, okay, on the final, it's 3 variables. So if you need a truth table, then this is, well, this part is what it would look like always, right? And I want you to start at 0. There's no hard and fast rule about that. But for me to pick through your work, it's just easier if you start at 0. Technically, you could reverse these, start at 1. Crazy. But I don't want you to. We say that 2 functions are equal, right? F equals g, so f is a function, g is a function, a Boolean function, if the columns of f and g in the truth table are exactly the same. So we'll keep that up our sleeves, right, for going through these Boolean algebra laws. Now I brought some of the formula sheets. We haven't used the last page yet until today. So if you need a copy of the formula sheet for later, I pasted it into the notes, but there they are. Yeah. So these laws, and they go on to the next page, are on your formula sheet. So that's nice. So let's just have a read through. Now, one of the notes I want to make here is that the only difference here is that these are Boolean functions. Whereas if we have x's and y's, we call them Boolean variables. If you do a comparison, right, the complement of f is f, while the complement of x is x. So they have the same laws. So I could have just given you one, but it had both, so why not? And then this is just the name of the law. I'm going to be referring to the property numbers. For simplicity, property number. Right, by property 5 or whatever. So I'm not going to call it De Morgan's laws or anything like that. So we already talked about, and I think for simplicity, let's only talk about the Boolean functions, but just remember that it applies to the Boolean variables as well. You're just dealing with x's and y's instead of f's and g's, but they work the same way. So De Morgan's laws says that, okay, if I have the complement of f plus g, then that's the same thing as the complement of f times the complement of g. Okay. You might remember De Morgan's laws from logic, where, what did we use? We used A or B. So did we use the V or the U? Can't remember. A or B, I'll keep it nice and vague like that, is the same thing as the complement of A or B is the complement of A and the complement of B. Right. That was De Morgan's law before. And so here we read this as or and this as and, but we just established that, so here this is or and this is and. Or was addition and was multiplication. So it translates into Boolean algebra where we have f or g, the complement of f or g is the complement of f and the complement of g, right? Multiplying. Same thing going in reverse, right? The complement of f and g is the complement of f or the complement of g. Property 3 says that, okay, I can reverse the order and it stays the same. F plus g is the same as g plus f. That's good to know. And same thing for multiplication. The associative laws still apply. So f plus g plus h is the same thing as f plus g plus h. And same thing for multiplication. The wild card here, I think, is this guy. F plus g times h is going to be the same thing as f plus g times f plus h. And we're going to confirm that with a truth table, right? So what are we going to do? We're going to set up our truth table of f and g and construct both of these columns, right? The column of the left-hand side and the column of the right-hand side. And then at the end, we're going to make sure that they have the same values, the same truth values. And then we'll blindly accept that it also works for f times g plus h is the same thing as f times g plus f times h. Idempotent laws, we already established that if we said x plus x is x and x times x is x, right? But it can work for the functions as well. F plus f is f and f is f. So many laws. This 0 and this 1 are not from the Boolean function. So these are always 0 and always 1. Oops. Always 1. F plus 0 is f and f times 1 is f. Now we're going to use this quite a bit where we multiply by some convenient value of 1. And where we get that from is from the next property where we have f plus the complement of f is 1. So if I want to multiply by some convenient value of 1, usually what we do is we take f plus the complement of f, right, multiply it, and that's technically multiplying by 1 because of this complement law for property 8. Same thing if I want to add 0, which is also convenient, right? Multiplying by 1 or adding by 0 are convenient ways of manipulating an equation, right? You're not really changing anything, but you are adding things that you might need. And so here, if I have f times the complement of f is 0, I could add that and it would still be adding 0, which is fine. The dominance laws say that f plus 1 is 1. So as long as there's a 1 involved in the addition, then it's 1. And as long as there's a 0 involved in the multiplication, it's 0. And the absorption laws, another kind of weird one, I guess. F plus f times g is f. And f times f plus g is f. And as our example, we're going to use a truth table to confirm property 5, just like Just like I promised. Grab the whole thing. Let's only do this top one. You can do it for all of these, but I mean, this second column is going to look exactly the same. How many variables do I have? I have F, I have G, and I have H. So I need to make a truth table that has F, G, and H, which means I have 2 to the power of 3 possible combinations. So again, I have 0, 0, 0, 0, 1, 1, 1, 1. And oops. I'm going to bump it up just a smidge. Okay. Same thing, but alternating quicker. 0, 0, 1, 1, 0, 0, 1, 1. Now alternating every other one. 0, 1, 0, 1, 0, 1, 0, 1. Now we're ready to start. What are we going to do? We're going to construct each of the components that we need. I'm going to start with GH. So that's a quick win. All right, and then I'm going to make F plus G separately because I don't want to get bogged down. And then I'm going to make F plus H separately, and then I'm going to do those two multiplied together. Right, so really break it down. You only want to do one move, essentially. So GH. G times H, luckily they're right there. I'm multiplying, so I get 0, 0, 0, 1, 0, 0, 0, 1. Cute. F plus G, not H yet. F plus G, 0 plus 0 is 0. 0 plus 0 is 0. 0 plus 1 is 1. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 0 is 1. 1 plus 1 is 1. And 1 plus 1 is 1. Same thing for F plus H. F plus H is 0, 1, 0, 1, 1, 1, 1, 1. Just check. Okay, good. Now we have our components. We're not done, but we have our components. So now I can build the left-hand side, which is F plus G times H. I already have GH here. So what's nice about it being on paper, right, is that you can use your fingers. And so you would have a finger on F and a finger on GH and then move down so you don't get cross-eyed. It's harder on the iPad because it moves it around. To use my nails. Oops. And a pen. There. 0, 1. Oh my gosh. After all that, I was holding on the wrong. I was looking at H. GH. Okay. 0, 0, 0, 1, 1. And the rest are all ones. Hopefully I didn't add one. 1, 2, 3, 4, 5, 6, 7, 8. Phew. Should have put lines on there, I guess. Clean it up a little bit. Now, F plus G times F plus H. Way I can pull this off. 0 times 0 is 0. 0 times 1 is 0. 1 times 0 is 0. 1 times 1 is 1. 1. 1, 1, 1. Looks good. 1, 2, 3, 4, 5, 6, 7, 8. Since these are the same, they are equivalent. Whee! Okay, nice. So like truth tables in general, just gotta keep it all straight. And I definitely should have been using lines. It's hard to read across. Okay. Any questions about that one? No? Okay. What about property 10? We're going to look at it in terms of Boolean variables. So the X's and Y's, just so they're not so uncomfortable or so unfamiliar, I should say. And then we're going to show that it's true mathematically, making note of the property used in each step, which is another way that we could have approached this if you don't like truth tables. So let's see here. Property 10 is this little guy. And let's just focus on the top one. X plus X times Y is X. So we're going to prove that that's true, citing which property we're using as we go. So first I'm going to write this out. X plus X times Y is X. Where I'm going to start is, well, it's hard to do anything to, I guess you could, but yeah, you really could. But I'm going to start manipulating the left-hand side because it feels more accessible. So I'm going to start at X plus X times Y is, now what I'm going to do is I'm going to multiply the X by 1 by a convenient value of 1, or just any value of 1. Which I'm allowed to do by property number. I'm allowed to multiply by 1, and it stays the same by property 7. And I'm just going to scoot this up. Scoot, scoot, scoot. There. Give myself a little bit more room. So now what we have is I have X times something plus X times Y, and we didn't look at this property, right? But if I have X times something plus X times Y, I can pull it out. So that just means I can extract it a common F by property 5. So this is X times 1 plus Y by property 5. The 1 in addition overrides the 1, whatever Y is, right? 1 plus 0 is 1, 1 plus 1 is 1. So regardless, 1 plus Y is just 1. So I have X times 1, which is property 9. Just give it to you. And then by property 7, again, which we already used, right? If I have X times 1, well, that's the same thing as saying X. So you could do that, but often, to me at least, I don't look at this and say, oh, there's an obvious thing I could do here to manipulate it to make it look like X on the right hand side. So then you can use the truth table and you can set up your truth tables and you can show that those two columns are the same, and that's going to be the same thing. But it's good to practice writing out kind of which property you're using. Makes you think about what properties you use. Let me just make sure. Okay. I caught a typo. So if you're working on the one that's posted on Moodle, I haven't fixed it yet. This should be a Z. So we want to simplify this expression using Boolean algebra laws and indicate the properties used at each step. And so I'm going to rewrite it out because it's very small. Wx plus the complement of x times z, and then the complement of all that plus y plus the complement of z. Now, when we say simplify here, we want one order of, well, I shouldn't say order, but ideally at most one thing of w, one thing of x, one thing of z, and one thing of y, but in the appropriate order, right? And that can be either on its own or the complement, but just one thing. Only one of each term. Because it's quite large, I'm going to put my equal sign below there. Okay. First thing I'm going to tackle is the complement of x and z. Okay? Because it's just kind of weighing me down, and maybe there's a way to pick this apart or to simplify it. So that's the first thing I'm going to do. Now, to do that, I have to use De Morgan's laws, right? So the complement of x and z is the complement of x, or the complement of x, or the complement of z, right? To split these apart. So if we go back to where is it? De Morgan's laws here. We have this. Nope, we have this. Nice try, Emily. X and y, the complement of that is x. The complement of x plus the complement of y. So I have wx plus, and how about I use green for the change that I made? The complement of x plus the complement of z, and then everything else I'm leaving alone, plus y z bar. And this is by property number 2, we established De Morgan's laws. Okay, there is a quick win, because now the complement of x we know is x by property 1. So let's do that. The complement of x is x plus the complement of z plus y plus the complement of z. That was property 1. Aha, now I don't need these brackets anymore. In fact, I didn't really need them because I'm just adding. What else could I do? I was gonna lump these together, but in my notes, I hold off. So let's hold off because I don't want to trip myself up. So this, I have an X here and an X here. So I'm going to regroup these, not really changing anything, but I'm going to create these groups WX plus X, and I'm going to group them like this, plus Z bar plus Y plus Z bar. I have property 4. Property 4 says that I'm allowed to regroup. So A plus B in brackets plus C is the same thing as A plus B plus C in brackets. Okay. But then if I have something times X plus X, then that just morphs into an X, and that's by property 10. So let's go back because that's the one that we looked at, right? If I have X plus WX, right, or WX plus X, then we just proved that that becomes X. So this becomes X. Oh, that's the new one, so I'll do it in green. Plus the complement of Z plus Y plus the complement of Z, and that's by property 10. Now I don't need those square brackets anymore because they're not really doing anything. But what I do see is, okay, so I've got one thing of X, that's great. I have a thing of Z and a thing of Z. So I'm gonna need to simplify that, and I have a thing of Y, a thing being itself or the complement, right? Doesn't matter, some version of it. So we need to get it down to just one thing of Z. So what I'm going to do is I'm going to group those together and see if there's anything I can do. So X plus, and then I'm going to group these, the complement of Z plus the complement of Z plus Y, which is property 4 again, where I'm allowed to rearrange things if I'm adding and multiplying, and it doesn't change value. Where we started today, we said that, okay, if I have X plus X, it's X, right? And so now I have the complement of Z plus the complement of Z, which I can replace with the complement of Z. Oops. X plus the complement of Z plus Y. And that's by property 6. So now it's simplified. There's only one thing. In fact, we dissolved the W. The W is gone, so it's extra simplified, basically canceling. Okay. Good thing those properties are on your formula sheet, huh? Some definitions: if f is a Boolean function on n variables, but remember we're going to stick to 3 or 4, but it applies in general, then each term, we've been using xyz or wxyz, xi I could use, is called a literal. I almost used the term earlier and then realized I hadn't defined it yet, so good to know. Right, and so here when we're simplifying, oops, I guess that works, but when we're simplifying, right, we can only have each literal appearing once, right, is what it means to simplify. Now, a term of the form, so if we're multiplying y1, y2, all the way up to yn, right, where yi is equal to xi, or the complement of xi is called a fundamental conjunction. So some multiplication of all the possible literals. So here, this is a fundamental conjunction, which is going to lead us to the DNF, which is what we're going to be using. And so a representation of F as a sum of fundamental conjunctions is the disjunctive normal form for the DNF of F. So to clarify, the literal is, let's say f, x, y, z has three literals, x, y, z. Each of those are literals. A fundamental conjunction would be x times y times z, or some mashup of complements, right? For n equals 3, it's going to look like this. And then the disjunctive normal form is going to be a sum of fundamental conjunctions. So it's going to be some mashup of x, y, xyz plus xyz complement maybe, or x complement y z, or something like that, right? And so it's going to be a sum of fundamental conjunctions. And that's the disjunctive normal form. And you do have to write something in disjunctive normal form on the final exam. Heard it here first, or maybe not even first, but you will have to do this. But once you get the hang of it, it's not so bad. Remembering that each fundamental conjunction has to have each of the possible variables in it. That's where multiplying by 1 or adding 0 comes in really handy, right? Without further ado, now I've called this example A, and we will refer to example A later. I'm going to copy and paste from there, or from here, but just so you know what does she mean, example A? Okay. So even on Monday, we might refer to example A. We're going to find the disjunctive normal form for some function, and just ignore that, where it's a function on 3 literals, right? And it's xy plus the complement of x times z. So what we want to do here, to clarify, we want to rewrite f of x, y, z as a sum of x, y, z's, right, fundamental conjunctions. Two ways we can do it. We can do it using truth tables or using the properties. Well, let's start with the truth table because it's more approachable. We've worked with truth tables before. It has been a while, but we can do it. And so I'm going to make a note here. We can solve this or find the DNF 2 ways. The first one is to make a truth table. Make a truth table for F and use the combinations of x, y, z that yield values of 1 in F. Let's do the truth table, but I'm going to need a page here. I had a page. Pardon? Oh, yeah. Okay, I'm going to remind myself what it is I want to be doing. First off, x, y, z. I have 3 literals. And so now I'm going to have 2 to the power of 3 possible combinations of these things. And so let's set that up first. X, Y, Z. Same setup as always. Hey, now I have these nice lines. I wonder if I can make them smaller. I can. There, that's probably good. Apply. Whee! Weird for me, but great for my truth table. It's gonna make my printed or my PDF notes look amazing, because for some reason it removes the lines now, so it looks like I've got this sort of straight writing. Wow. Well, I don't. Okay, so let's set up our starting truth values, starting at 0 because that's what I want. Prefer 0, 0, 0, 0, 1, 1, 1, 1. Now quicker mashup. 0, 0, 1, 1, 0, 0, 1, 1. 0, 1, 0, 1, 0, 1, 0, 1. Okay. So now I'm going to make, I need a column of the X, Y. I like to make a column of the complement of X before I make the complement of X and Z, because otherwise I'm having to do the conversion and the multiplication at the same time, and that's really difficult for me. So let's see here. Let's make X, Y first, kind of as they appear. X, Y is 0, 0, 0, 0, 0, 0, 1, 1. Nice. The complement of X, 1, 1, 1, 1, 0, 0, 0, 0. Put that in its own column here. Now, complement of X times Z. 0 times 1 is 0. 1 times 1 is 1. 0 times 1 is 0. 1, 0, 0, 0, 0. So close. This is one of those things. It's tedious, but it's kind of fun to get the structure. And so now we're ready for XY plus X bar Z, or the complement of X. X bar is technically the mean of X, and so I'm not going to do that. I'm going to try not to. XY plus X, the complement of XZ. I have 0 plus 0. I need to keep my eye on the ball here. Is 0. 0 plus 1 is 1. 0 plus 0 is 0. 0 plus 1 is 1. 0 plus 0 is 0. 0 plus 0 is 0. 1 plus 0 is 1. And 1 plus 0 is 1. Aha. We have 4 combinations of x, y, z that yield true values. So how do we use that? So now we're going to say that this is from x being off, y being off, and z being on, right? And so this is from just z. This is from x being off, y being on, z being on. Oh, I just realized I am asleep at the wheel here. Not just off, but the complement of w and the complement of y, z. Sorry. Because it has to be the fundamental conjunctions. W. I do not know where that came from. Like I said, I'm asleep at the wheel here. Yikes. Which means our conjunctive, our fundamental conjunction. Ugh. Which is what we're after. Is the one in the pink. Okay, now I'm ready. X is off. Y is on, Z is on. For the last one, X is on, Y is on, Z is off. For the final one, they're all on. Our goal, or what we were asked to do, was to find the DNF, the disjunctive normal form, which is F as a sum of fundamental conjunctions. And so what we have is we get, oops, zoomed in too much. So then we can write F of x, y, z is the sum of these fundamental conjunctions. So I'm just going to copy these out. You don't have to write them out here. You could just add them, put them in your sum right away, but I wanted you to see where they came from. So I have x, not y, z plus not x, y, z plus x, y, not z plus x, y, z. So this is the disjunctive, oops, spell it wrong. Disjunctive normal form of F. If you want to, you could always use that method, right? But here's another way, right? We said that there are 2 ways to solve this. So you can make a truth table just like we did, if this works for you and you enjoy that, then that's great. Just do that. Okay? Because you will have to find the disjunctive normal form on the final exam, right? So have one way that works for you. Here's the other way. 2. We're going to rewrite f of x, y, z with all 3, right? Same idea. All 3, because we have the same goal. All 3 variables in each product term, right? Which makes it a fundamental conjunction. How we're going to do that is by multiplying by 1. By multiplying by 1. So I'm going to bring in and just remind ourselves what 1 is from the formula sheet. Where is it? Oh, I think we're going to use this one. Or I know we are. I don't want that always. Guess it makes it obvious that I stole it, but where it came from, but there. Right, so if we have, now we're going to work with x's, y, z, so it doesn't matter which column you look at, but let's look at this one. So x plus the complement of x is 1. Okay, so that's going to be our moneymaker. So where do we start? F of x, y, z. Let's start with the original function, xy plus the complement of x times z. What I'm going to do is I'm going to create spaces for each of the literals, right, for x, y, z, and I'm going to keep them all in the right order. Technically, it doesn't matter which order you use, but I'm always going to use alphabetical order because it'll make a difference later. And so I want you to do the same thing. So what we're going to do is we're going to make a space for a z, right? Kind of z goes here, plus I have the complement of x, but I'm going to create a space for some version of y here. And then I have z already. Now, in those spaces, I'm going to add z in this first space. I'm going to add z as a 1, which means I'm going to add or multiply by x plus the complement of x, which in this case is going to be z plus the complement of z. So this becomes xy times the complement of, z plus the complement of z. X, the complement of x, and then do the same thing for y, y plus the complement of y, but multiply times z. And maybe I'll do these in different colors just to emphasize. But green. Okay, so now I can apply the distributive property, which is, okay, I can expand into these brackets by taking xy times z and xy times the complement of z. So I'm gonna get xyz plus xy complement of z. I can do the same thing. Gonna get a little sneaky. So usually I would move this, the complement of x times z on one side and then distribute it. But because I want to preserve the order, I'm not going to do that. So gets a little bit weird to look at initially, but x, the complement of x times y times z plus the complement of x times the complement of y times z. Do we dare compare these? First, I'm going to look for duplicates, because if I have duplicates, then I can eliminate them. I don't see any. I'll add that here. Check for duplicates as they are not needed. But if we compare this to what we found using the truth table, really hoping this pans out for my sanity. So here, I'll change this, the color of this. From the truth table, things have been rearranged. Let's bring this down here. Copy, paste. I see that this one's over here. This one is here. This one is here, and make a real mess and go like that. Ugh. Should have cleaned that up somehow, but oh well. So they're the same. So two ways. I personally would lean this way, but I also feel very comfortable in truth tables, and I don't mind a little bit extra work, kind of as long as I can be sure that I can get to the answer. And so practice both ways is what I would say, and figure out which one you prefer, because maybe once you've done enough practice with these, you can always check your work using a truth table, right? You can always confirm that you did the right thing, because you're going to end up at the same answer, the same disjunctive normal form. Pretty cool. Ready for another one? So another one that we're gonna refer to, example B, I called it. Find the disjunctive normal form, or the DNF. Uh-oh. 4 literals. Do you want to make the truth table? 16 rows. No, I don't want to. So many zeros and ones for me to read. So we could, I'll make a note. We could use a truth table, right? And we would get the same results using it, but we would need, oops, 16 rows. Ugh. So let's flex our muscles with multiplying by 1, see how it goes. I'll write it out again. G of W, X, Y, Z, right? It's this added W that makes us need 16 rows instead of just 8, just 8. All right. I'm gonna write it out bigger here. W, X, Y bar plus W, Y, Z bar plus X, Y. And then I'm gonna just make space for the literals that are missing in each fundamental conjunction. So I have W, X, Y bar blank plus W blank, Y, Z bar. I'm adding steps. You don't have to add these steps, but I want, this is only our second example, so I want to really show where it came from. Plus blank X, Y blank. I'm running out of room. So this is going to be a Z. This is going to be an X. This one's going to be W, and this one's going to be a Z. Making note to myself. And then I'm going to multiply by 1. Same trick that we used earlier. And just because I'm going to need more room. W, X, Y bar times Z plus the complement of Z plus W times X plus the complement of X times Y times the complement of Z plus W plus the complement of W times X times Y times Z plus the complement of Z. Just barely squeezing on. All right. We can distribute this nice and slow. Why do I say nice and slow? This is all fine and happy, but what about here? I'm going to distribute one of these things and then distribute that onto the other one. Probably distributing the W's first, treating the Z plus the complement of Z as one thing for a little bit, and then distributing. Okay, W, X, Y bar, Z plus W, X, Y bar, Z bar. One done. Many more to go. Plus W, X, Y, Z bar plus W, X bar. Ugh, don't like saying that, but I'm lazy. Y, Z bar. And to indicate, so whenever I have to go across multiple lines, I bump in my plus a little bit, so for readability, right? And so I put my plus sign here, and then I have W, X, Y, Z plus the complement of Z, right? Keeping it as one thing for a little bit longer until I'm done with the W's, plus W bar, X, Y, Z plus Z bar. Finally, I can distribute these two, these final two, and I am gonna cheat and copy paste. I don't want to write all that out again. And I know that's cheating. W, X, Y, Z plus W, X, Y, complement of Z, plus not W, X, Y, Z, plus not W, keep my eyes straight here, X, Y, not Z. Keeping them in alphabetical order makes it a little bit easier to look for duplicates. Are there any duplicates in here? Ah. Any others? I don't see any others though. Thank you. Because man, is that hard to look at. Okay, so then I'm gonna rewrite this out, excluding one of them. You have to keep one. W X Y bar Z plus W X Y bar Z bar plus, I'll keep the first one, W X Y Z bar plus W X bar Y Z bar. Uh-oh. Oh, I had all the space in the world up here, didn't I? So lofty. Really emphasizes this desk has that rattle, which is super annoying. Yeah, it's whenever I lift my hand off the screen is when it complains. Now I have definitely lost my place. Let me find it again. Boom, 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 boom. Probably shouldn't say that. It's a song. W bar XYZ plus W bar XYZ bar. Easy as pie, right? Yeah, that can happen. So now, aren't you glad that there's only 3 literals on the final exam? I told you you'd be happy about it.
I understand what's happening, but just like keeping track of all this.
Yeah,
it's you mess up once.
It'll follow you, yeah, the entire way. Yeah, you forget one bar, right? And then you're hooped. Yeah, so you want to take it nice and slow. But what's the benefit of this? Well, we could give them binary labels. If they're on, if they're off. So I should clarify that this is the DNF of G. And I think that you deserve a sticker. You got it. But only if you got it. If you got this DNF. You did. You know you did. Okay, so listing Boolean variables in alphabetical order. Okay, so that's going to be important now, because if we give it binary labels, which is what we're going to do, then 001 has a different meaning from 010, right? And so that's why it's very important that you keep the appropriate order. So that's why I say it doesn't necessarily have to be alphabetical, but just as a rule, we should make them alphabetical just to match them up. So if we keep them in alphabetical order, W, X, Y, Z, we can define any row of the truth table with a binary label. So here we've got an example of 3 variables, X, Y, and Z, right? So we've got our basic truth table set up of X, Y, Z, and then we have 0, 0, 0 is our binary label, which means 0. 0, 0, 1 is our binary label, which means 1. 0, 1, 0 is 2, and so on and so forth, right? And so we can set up this table, and then what we can do is, instead of talking about, well, I guess we have 4 up here, but instead of talking about, for example, instead of talking about X, Y, Z complement, for example, this is going to be the same as 1, 1, 0, which you can find here. 1, 1, 0 is 6. So we could replace this whole thing with 6. Or maybe I'll do this. Which is just a shorthand for, right? So then we don't have to, well, we need these, the disjunctive normal form, but then so that we don't have to read this ever again, we can communicate the same information with binary labels. In fact, the value base 10 of that binary label. So here we have the DNF. I really hope this is what we got. Pretty sure, but let's just check from example A, so I didn't muck it up at all. Well, here, hodgepodge. We decided they were the same, so I'm going to copy this one. Just confirm that we did get it. Wow. Even in the same order, X, Y, Z, X, Y, not Z, not X, Y, Z, not X, not Y, Z. Phew. From example A, we found that DNF. So now I can rewrite this as f of X, Y, Z is, and I'm just going to paste that in again. And what I'm going to do is I'm going to rewrite this as 1, 1, 1, binary. 1, 1, 0, 0, 1, 1, 0, 0, 1. If it's the complement, it's off. If it's not, it's on. And because I am not very good at converting, I use the table. Which, if you set up your truth table the way we usually do, then it's relatively quick, because then you, as long as you start at 0, then they're just going to increase by 1 as you go down, right? So just follow the same structure that we always do, and then you can have these binary labels accessible. Right? And so here, this 1, 1, 1 is 7. 1, 1, 0 is 6. 0, 1, 1 is 3. And 0, 0, 1 is 1. So we've got these binary labels And then what we do is we convert them to values that mean something to us, not computers. And what we do is we write the DNF in terms of the binary labels like this. So I've got f of x, y, z is the sum, because remember, it's the sum of each of those fundamental conjunctions. And then here's the min terms, which I've got defined down here, but let's just take it for what it is for a little bit longer. And then we list these values that we found, right? We're communicating the same thing as this hodgepodge, right? It's just, it's easier for us to read 1, 3, 6, 7 and then attach them to some meaning, right? Then 1, 1, 1, 1, 1, 0, etc. Okay, and so now, especially in our previous example, right, if we could just list this in terms of some sum of numbers, right, or the min terms is what we're going to call it, that's going to be easier to read, right? So so here 1, 3, 6, 7. Wow, I did it again. Just making a mess. Okay. So M represents the min terms. Now the min term is the product of n distinct literals, where each literal occurs exactly once. And so, but as long as you remember this notation, then you're fine. We can extend the truth table, right? I've got the beginning 8, but if we have 4 variables, we can just keep going by doing what? We could add a W out here and make 0, 0, 0, 0, 1. Nope, still 0, 0, 0, 0, 0. And then I'm going to copy this because I'm going to repeat it down here. Try to match it up. It's hard. Close enough. And they all get ones. 1, 1, 1, 1, 1, 1, 1. Boy, that's a rogue 1, 1, 1. Which means, in terms of our binary label, we're going to add a 0, 0, 0, 0, 0, 0, 0, 0. I could write these all out, but the key is 8, 9, 10, 11, 12, 13, 14, 15. And that's what we need. So now we can, I thought I'd need more room, so I punched it down to the end of the page. But we had, where's our DNF, our mega DNF? Copy. Don't need this, don't need that. Oh, fine, I'll put it on a fresh page. No, we want to go home. I know. Me too. Me too. Okay. Let's make some, come on. Space these out. Because what do I have to do first? I'm going to write these out as 1, 1, 0, 1, 1, 1, 0, 0, 1, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 0. All these match up to something up here. So then we can represent it as the sum of the min terms. And because I don't have these here, you guys are whizzes with this stuff. I've got the ones that start with 0 because they're in our table. 0, 1, 1, 1 is 7. Gonna go for that. 0, 1, 1, 0 is 6. The other ones, 10. Nice.
No, top right.
Wee. This one? Okay. I'm gonna go with 15 for the last one. Has to be all ones. So we only have 3 left. Okay, let's see what we can do here. What was it? Let's start with 1, 1, 0, 1. You lost me. 1, 1, 0, 1, 13. Nice. Should have just listened. 1, 1, 0, 0. Nice. 1, 1, 1, 0. I knew it. You guys are so good at that, and I am not. I know, right? Do you know what's so funny though? I was talking to Joya, because she taught it. So I taught it, and then I gave her my notes, and she taught it, and then I was talking about how you guys have already been doing it forever. And I was like, I don't remember that being the case last time I taught it, which was like way back in 2020. And she was like, no, they were acting like it was the first time they'd seen it. So I feel like they've made a change and I just wasn't aware. Yeah, but it used to be, can you imagine? It used to be the first time that people would see it. Is the min terms of, now I'm just blabbing. And then I just list these, and preferably in increasing order. So 6, 7, 10, 12, 13, 14, 15? Question mark? I'll count them. That's a good place to start. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. Hey. There you go. Disjunctive normal form. Pretty fun. Fun way to spend your Friday. If you have any questions, let me know. Otherwise, I'll run down and print you off a copy. Sorry, Brent. I'll see you on Monday for some Karnow maps, which is just an extension of what we did today.